quantum mechanics is the most successful theory we know. It can predict things to 9 decimal places, and you measure it, it's there. So, excuse me, there's really something to it. But as the Nobel laureate Richard Feynman said, nobody understands it. So there are 3 sort of camps of interpreting how this works. One is that there are hidden connections between our mind and the physical world.
This is how you're explaining quantum mechanics, or
quantum mechanics.
Because I've never understood it in the first place. So
well, and I'll hopefully tell you a little bit how we understand it. But there's this theory, it's called hidden variables, and so somehow our minds were in sync with these hidden variables, and that's how we're able to then get a measurement out of something. But the universe in that case is pretty much like Newton's, very mechanistic. And you have cause and effect just like normal. But we just don't know everything is kind of what it's saying. That's pretty much been disproven by something called Bell's theorem. Another way is what Everett had, and that was that when you do a measurement on something, so we always go to measurement because quantum theory is a theory of how to do measurements, really. And when we measure something, you have to interact. And so the example would be if I put out my palm and I said, can you touch my palm without my palm touching you? You can't do it, right? You have to interact. And same thing in the quantum world. We have to interact in a measurement. And measurements change the system. They cast the system, we say, into different states. So anyway, but measurement acts on the system, and it should act back on you. And so Everett said, so if it acts back on me, then I am a subject like the kind of stuff I'm measuring. So we're going to go to Schrödinger's cat. And Schrödinger said, okay, if you take a cat, put it in a box, and have a vial of prussic acid and a hammer poised above it, and the hammer can fall by a trigger from a radioactive nucleus, there's a chance of emitting radiation so that in an hour, there's a 50-50 chance to trigger the hammer. Okay, so it's just to try to get some probability in there. So you have this cat, has a 50-50 chance to be dead or alive in an hour. And then you say, you cover the box up, you put it in your corner of your room, and you say in an hour, without looking, is the cat dead or alive? And quantum mechanics has to say it's both dead and alive, because you do not know until you take a measurement. The measurement will be the act of taking the cover off and seeing it and saying, oh, it's alive or it's dead. But quantum mechanics says it was both dead and alive. What happened to that part when you see it's alive? What happened to the part, the wave function that said it was dead? Well, it becomes a ghost kind of thing. So in this idea of it, that hidden variables said, we control what the outcome of the cat, really. And it's our minds interacting that when we open it, it's going to be alive, for example. And as I said, that's been discounted. Everett's, which I thought was really creative, said, you look at the cat, and when you open it up and the cat's alive, the universe splits and you split. So
there's a scenario where the cat's dead and a scenario where the cat's alive.
So you split to 2 universes.
Okay.
So we start to get a multi-universe. So anytime a decision, a measurement, anything is made, the universe splits, which means there's
infinite
Google number of these, which is kind of crazy too.
Right.
So people don't like it, that interpretation for, I'd say, that reason.
When you say people, you mean the scientific
scientists,
community?
Scientists. Okay. The kind of people
for you, that's just for you, it's just people.
But the interesting thing about it is that we are subject, just like the cat would be a subject. So it's this: we have to have a consequence of doing a measurement. So, but the standard interpretation was called the Copenhagen, and that got ironed out by a couple of conferences in Europe with the leading physicists of the time. I mean, it's just, you had Bohr and Heisenberg and Madame Curie and all the giants in the pantheon of physics were there. It's just, and that doesn't happen anymore, by the way.
Right.
But it's just amazing how they put the framework. And the framework got to be as, well, we can't say the outcome for one cat. We have to do, say, 100 of these cats. And then after an hour, 50 of them will be alive, 50 will be dead. It's all probability. Okay. So that is the standard, and it works, and we do that. And it says don't ask questions, but physicists like to ask questions, especially ones that push the physics towards metaphysics. So we want to know why. I mean, there's a why there yet too.
Right.
And we're approaching it because the other thing then that we've discovered is in quantum entanglement. And that's going to be where particles can be, when they're created, I like to give an example. There's one particle, a mu meson, neutral pi meson. And when it decays, it emits light. But it has to emit two particles of light in opposite directions because momentum has to be conserved. So if it's at rest, they go off in opposite directions. But now the idea is light has another characteristic. It's called spin, but you can think of a direction that some entity of it's pointing. And we also know that has to be conserved. So if you measure that spin of one of the particles of light, a photon, and compare it to the other one, they always have to be opposite. So we've done experiments to measure, and they're correlated. They're all separate. So then what they did was saying, okay, let's put them so far apart that when you measure the spin of this one, there's no way light could get to that one before you measured it. You measured it first. Mm. And we find out they're always opposite. And so we say these two photons are entangled now from when they were created. And it's not that their position was set that I'm going to be this way, you're going to be that way. It's got to be all directions possible until you measure. And then that one's opposite. It's always going to be opposite. So it's like they're connected. It's like if this one's twisted to here, that one twists, but through space and time. Over, I think that Chinese have done this with a spacecraft and on Earth. So that distance, they could still see entanglement.
What does that mean? Like, what is that?
Well, that's what we're beginning to explore.
Order to what does that order mean? Because there's order there.
Yeah, there's a lot of order there. Well, I like to look at it as if we go back to the Big Bang, everything was one, all the matter came out of energy. Is everything entangled? Are all particles, that make up atoms entangled, which means we're entangled or something.
Right, we're all the same. We're all one.
Yeah, we're all one. Yeah,
right.
So that's kind of interesting philosophical question. Physically, we turn to how we can use it, and it's going to be used for quantum, or has already been used in quantum encryption, so that there's ways of sending keys through things to entangled photons that other people wouldn't be able to read. And then you've got a key to decipher something to get your information out.
I can't even wrap my head around the practical applications of that. Would that require, obviously, programming? We're talking about for programming.
And usually some source to create the entangled particles. Right now, we've been using light most of the time. There are particles, I guess. If we could do electrons that physically travel in wires, that would be quite interesting to see if they could maintain their entanglement. Because if it interacts with something else, you lose the entanglement, to be honest. So
yeah.
But we don't know how information is transmitted faster than the speed of light.
Right.